So hello everybody, I'm Andy Hooper from the University of Leeds. I'm going to be giving you a final lecture today on time series InSAR. So please interrupt with questions as you go along. Keep me awake. Okay, so just a few slides on the motivation for why we do time series. We normally turn the lights down, but did everyone do okay? Very good. Okay, so you've already seen interferograms hopefully like this this morning. Maybe you've already been making interferograms like this. But this is what I would call a kind of really nice interferogram. It's nice for a few reasons. First of all, there's really good correlation, so there's very little noise. So you can really see the fringes, count up the fringes almost by eye. So it's really nice. The other thing is, the signal is really dominated by deformation. So you can take this interferogram and process it alone and actually get the information you want, essentially deformation. So this is great. First of all, you have to of course count up the fringes, which is based on that process. So you learned about this morning as well. In principle, that's quite simple, right? You count the fringes. In reality, it's tricky. You have a noise, you have this counting the fringes process. Okay, so here's maybe a more typical interferogram. So there's an interferogram here that has some signal, some interesting signal. In this case, it's partly deformation, but it's also got a lot of noise. So that's partly decorrelation noise, which is causing this sort of speckle in the colours here. But there's also some spatially correlated noise as well, mainly due to the atmosphere. Then you might have interferograms like this, which look like almost complete noise. So this is due to decorrelation, again, but it's more extreme. So we used to get a lot of interferograms like this with the older satellites. Sentinel-1 satellites, more modern satellites. You get fewer of these because we have we're able to make programs much shorter. Current time free. But nonetheless, you might still come so you do still come. So this is kind of the motivation why we might do time series InSAR. First of all, it allows us to better select the coherent systems, so to get rid of some of the noise. It also allows us to estimate some of the spatially correlated errors. So this is chief in the atmosphere, especially in some of the older satellites. We have a lot of orbital errors, just due to not knowing exactly where the satellite is at the time. So it's due to that. So we can basically take this time series and we can filter it in time and space to try and reduce the signal. There's some other areas we can get rid of as well. You've learned, I hope, that you have to subtract off the topographic signal with every interferogram, but there's always some of that signal left. We don't have perfect topography, so we can actually reduce that even more using this approach. We can do better phase unwrapping. As I mentioned right at the beginning, phase unwrapping can be problematic. Times this is counting fringes, so by having more data, that's the job. And a final point, which is not really relevant if you're only interested in geophysical signals, more relevant if you're interested in infrastructure, is you can actually get sub-pixel resolution, so it can be better than the normal resolution of the programs. You can try and locate points of the within kind of meter type. Okay, so that's why we do time series analysis. Just to sort of demonstrate that point, this is standard interferograms that I showed you already. On the right, it's kind of using a time series assisted scattering analysis. I don't know what that is in a while, but that's a time series approach. So what's different about this is that first of all, only the pixels which are coherent are being picked out. So you can see, actually, for this left-hand one, it doesn't make a huge amount of difference, quite coherent anyway. For the right-hand one, it makes a much bigger difference. So where it looks like it's nearly all noise, as it turns out, you just look at the slightly simple. And the other point is that you follow this through time series analysis, you start to spit out kind of signal we're interested in. So in this case, it's a slow signal in subduction interface. You can separate this out from things like atmosphere and errors in your elevation. Okay, any questions on the motivation before I dive into this? Yes.
So this isn't like doing one interferogram here and one interferogram further like at a different time, sort of step. And this is actually using all of the takes, sort of even, using more data in sort of give any given idea about what happened in that time.
It's kind of both of those. So it is indeed taking lots of interferograms and now analysing them in some way, and actually just stacking them up is one way to try and extract the signal in a better way. But there are other approaches to analysing all of these interferograms. So maybe I'll answer your question.
Yeah, basically.
So I'll talk about the actual details of the way to go about that. Yes.
The more data could be with the problem instead of improving we don't have the coherence or something else.
Yeah, so if we add in more data, it's true that you might take one really nice program that was noise free, then include some which are really noisy. But actually, the way we go about analyzing more weight.
I faced with the problem that when I analyze the just sentinel A data, it was once in 12 days, it shows some gradual gradient movements, but when I combine the sentinel A and B, these gradient movements disappear. Could it be because of the data, the bunch of data, the number of data, high number of data, or not? I made some problems with the calculation.
Okay, it could be a number of things. So there are, I won't really get into this in this talk, but there are biases that come in if you combine some very short time period programs. So if you're just using A and B, you're making 6 data programs. So that can actually be biased. We're going to have a chat about that after. Okay. This is just a demonstration of kind of high resolution. This is not using Sentinel-1, the data you're using in just for physicals. These are from one of the expands high resolution. And if you're careful with your geolocation, you can actually get multiple points. So if you're interested in infrastructure, it's going to be useful for especially using high resolution. So what you see actually is deformation of buildings as they heat up. Hopefully, you would see it also if they were getting down. Okay, so there are kind of two broad categories of time series analysis. One is called persistent scatter, or PS, and the other is for small based. So I'm going to talk about both of these. In part one, I'm going to just focus on the persistent scatter. So to understand this, you have to understand what's actually causing the decorrelation. If you take a normal pixel, it's actually a resolution cell, like it's called, use pixel as kind of shorthand for resolution cells. You take one on the ground, of course your energy is coming from the satellite, it's bouncing off, scattered on the ground, it's back to the satellite. So what you actually get back at the satellite for one resolution cell, essentially one complex number one value of the phase the action for the whole resolution style. But it's actually the kind of sum, here the sum of lots of scatters on the ground, which gives you that signal. And the problem is, if these scatters move around with respect to each other, or if you look from a very different angle, then they add up in a different way. So this is just a simulation of 100 different acquisitions. And you can see the phase is just popping around. This is phase minus pi, pops around almost seemingly in a random way. These move around. So. And it's similar if you were to change the angle as well. So why might this happen? I mean, if your scatterers are due to vegetation, for instance, then if these are leaves and twigs, then you might expect it to move around between acquisitions. Okay. A persistent scatterer pixel, on the other hand, is a pixel that's dominated by one scatterer at least much brighter, significantly brighter than all the others. So then, even if all the others move around with respect to that bright scatterer, still maintain coherence. So you can see there's a bit of noise due to the other scatterers contributing as well, but overall you can trace that signal in time. So if that scatterer was to start moving, you can see that in the gradual change in the phase. Okay, so that's the principle of Pierce processing. How do you actually go about extracting them? Well, first of all, you have to make all interferograms with respect to one primary image. This, we used to call this the master image. I try not to use that terminology anymore, master. So, but one primary image is used with which to make all of them. No filtering is applied, don't worry about it earlier. Oversampling is preferred. The main purpose of this is to try and make sure that your white scatter is actually somewhere near the middle. But actually, it'll normally work either. And we try and reduce the interferogram phase as much as possible, so we do the usual things, which is minimize ambiguities. So you end up with a series of interferograms, something like this. So then if you saw something, do you see a pop like this morning already? Baseline plot. Yeah. Disagree with it. So on one axis is time, and one axis is perpendicular baseline. So this is did you hear about perpendicular baselines? So it's a difference in basically the difference in so each of these red circles represents one image. So this is the primary image here in the middle, and then each of these green lines representing an interferogram. So it's what you end up with in terms of the phase is the phase difference between each of the pairs. As I mentioned before, for the Pierce approach, all of these one primary. And here's an example of that. This is using 10^1 data. See that there's very high rates of substance. Each of these interferograms, you've got fringes. You look at the first one, the fringe rate is quite low. The last one down here, much higher. There's increasing substance. So the master date here in this case was prior to all of the others. So generally speaking, it doesn't have to be. In fact, try and pick one normally that minimizes the average time. Okay. So to understand the algorithms, I'm going to talk about two different algorithms for identifying these detectors. You have to drill down a little bit more into what's contained in the phase of each pixel. So you can break it down into the deformation due to the actual the phase change due to deformation. phase change due to differences in the atmospheric rate. Phase change due to orbit errors, and this is the fact you don't know exactly, but it's reduces a phase to image. The DM error that I talked about already, and then the kind of catch-all noise, which is going to include declination noise and as well. And you can identify PS pictures essentially by how much noise they have. So this noise term is what characterizes whether a picture is going to be a PS pixel. Although you think about these PS pixels as something being dominated by scatterer, practice, the way you characterize it. So if it is just a distributed scatter pixel, then you get a lot of noise, generally speaking. Okay, so I'm going to talk about two different approaches to this. There's this one which really relies on a kind of temporal model for how the phase evolves, so how the deformation will evolve. And then I'll talk about another one which is based on spatial correlation. So first of all, this temporal approach. So this is the original resistant scatterer type of algorithm. In fact, the very first algorithm is called permanent scatterer. This is trademarked, so everyone after that refers to persistent scattering. But nevertheless, they all have a lot in common. There are some small differences. Most PS approaches use the same approaches. So what you can see here is the San Francisco Bay region, here, and colour here is representing average velocity. So although you have a whole time series of images, you actually get a track time series of deformation per pixel. One of the things you can show is the average velocity. Shown here. Then I won't go into the details of why this means the Bay Area. Okay, so the principle behind this temporal PS approach is this. If you take two pixels nearby, back the phase of one to the other, you kind of cancel out the atmospheric and the orbit term. Okay, because the atmospheric signal is very correlated spatially. If you have 2 points which are nearby, they almost do the same change this. You kind of almost cancel it out. It's the same with the orbit. So then you're just left with your deformation, your DM error, and noise. And the idea is you can model these two terms. Okay, so both deformation probably can be modeled this way. Okay, I'll show you in a minute in which way. So first of all, you have to select what points you think are most likely to be good PS pixels. And as I mentioned already, this is really based on the phase noise. You can actually get quite a good proxy for that by looking at how the aperture goes. At least for pixels which have a very low phase. So there's this quantity over here called the amplitude dispersion, which is the standard deviation of the amplitude of the whole time series divided by the mean. This is per pixel. So you can calculate that for every pixel in a series of kilograms, and that's a reasonable proxy for phase noise. You can see down here for these low values, basically things are quite correlated. Below about 0.35, the phase length is correlated. So what you can do is you can pick out an initial network of points which have this low amplitude dispersion, which are likely to be existing. Make sure they're reasonably spatially distributed. You get a network like that. And then form these arcs or connections between neighboring points. Okay, so this is the idea of this is to track the phase neighboring points to reduce or almost eliminate atmosphere. Okay, so you can then take these phase differences, they're actually double differences, they're different in time and in space, and you can try and model these two terms, the left, deformation, and the mirror. And this is typically how they're modeled. So in this case, there's an assumption here that the deformation is steady state in time. Okay, if that's the case, then if you've got time on the x-axis and phase on the y-axis, you can basically fit a straight line at these points. Okay? But you have to take into account the fact that these data all lie between minus pi wrapped data. So you have to allow for the fact that you can add integer number of 2 pi in these points. So the actual straight lines being fitted here, this one, where 2 pi has been added to this point, and 4 pi has been added to these points. So it's not a straightforward estimation process actually to find the best fitting line. And in fact, if you allowed any number of integers, then you can fit every point down. So there's normally some assumption, you have to put some bounds of what's a reasonable amount of definition. Otherwise, you just huge deformation bits. Okay, but anyway, in principle, you can do this for every pair of pixels. You can do a similar thing for modeling the DM error as well. So in this case, instead of time on the x-axis, it's now perpendicular to the baseline. And it turns out that you expect the phase to be rated linearly perpendicular to the baseline. The equation is given here. Essentially, this is just a constant. Okay? So you take the slope of this, which is this constant, you can see the delta range term is in there. DM error. I should add, it's actually the DM error of the DM difference. Right. In practice, you have to do both of these things at the same time. That makes it even more difficult, actually. You can't just estimate velocity of the baseline separately. You really need to do two things. It's a two-dimensional problem. And you wrap data. It's not trivial to do. But you can do it. And the final step then is to integrate. So pick one point as a reference point, and then integrate these velocities and errors estimated from that point over your formula. Then for the value for the velocity and the DM error. Does that make sense? Here's an example of that. This is actually a very early study, I guess, for Las Vegas. So these are DM errors, some very high ones due to high buildings. These are the losses. So actually, Las Vegas, very long substitute. Okay, so having identified there's some adjustment there that has to go on while you're doing this integration. You can actually check for consistency. So, of course, you should be able to integrate by any path from the reference point to any other point. If the same value won't always be the case. The process of rejecting points which aren't very good. Once you've done that, you can then look at all the other pixels. Yeah. So once you've done that, you can look at all your other pixels and test to see what their flaws as well. By again looking at doing this modeling process and estimating. And the final step is what I mentioned right at the beginning: is you can try and get rid of some of these spatially correlated noise terms, which are basically act as a G, by doing some filtering into time space. This helps you to separate out definition. Okay, so I showed you this result already. This is the sample area. I'm just showing the velocities. So, in principle, there's a time series. It may not be complete steady state. You'll note, though, it's not working everywhere. So actually, the regions where it works really well are the regions where you have buildings. So this is the Bay Area itself. You can see there's smaller cities on the coast here. But in between, in the vegetated areas, there are breaking points. So this is, you might expect this, right? Because buildings with angular corners tend to have a good chance of having quite scattering. As that's not true in vegetated areas in general, you might expect to have more distributed. So that kind of makes sense, it's logical. So I just answered that question. But nevertheless, you might think that in some cases, you might get some natural scatterers that can also be brighter than the So there are a number of reasons why it might fail in that detail of it. You start off with all your pixels like this. You pick out your best candidates using some aptitude. And then you reject the bad candidates. So having done this sort of estimation process, detections between different pixels, you can reject those that are already consistent. This doesn't work if you have too few good candidates to start off with. So the problem is there that you have the distance between these good points become so great that your assumptions about eliminating atmosphere are no longer true. So they're too far apart, more than a couple of kilometers, then it's not going to work, and you can end up just rejecting it. And if you lower your bar too much as well to get more candidates, so you have more person you go to in the first place, then you end up with too many bands. So for it to work, it has to be the case that most of your pixels that you think are yes in the first place actually are. You get more than the number. If you get too many that aren't, then you also fail. The other reason it might fail is because actually you're modeling, you have to model the phase, the deformation in this case, and your model is inadequate. So if you're not really steady state, then you should also fail. So you can interpret what's actually deformation in noise. There's an example of this here. There's a landslide in Italy. See a few points around here outside the landslide area. Inside the landslide area, no points were picked, despite the fact there's a small village in this area. So lots of buildings. So none of those were picked because the points were behaving very erratically. Okay, so this is sort of motivating where I came into this. So actually, my PhD was trying to apply to volcanoes. I started off looking at the Storm Valley there back in the early 2000s. And I applied one of these techniques, PS techniques. And this is the result I got, so a little bit disappointing. It's a really nice, cool insignia over here. It's a small town here. But actually, where all the deformation is here, I had no. So I was motivated to try and find a different approach to try and pick out points, which may be low amplitude, still have they have rocks or whatever that still behave years. And also accounting for the fact that volcanoes don't tend to behave in very irregular deformation. Okay, so I worked on developing this different approach, spatial correlation model. Just talk about that a little bit. So the first step is the same. You just form a bunch of interferograms, all with respect to the same primary interferogram. This is where it differs. So this is the breakdown of the phase again, different terms, and so on. But what characterizes a PS tool is the noise, as I mentioned already. So in this approach, you just try and get rid of everything that isn't noise to characterize it. So the first thing is to basically subtract off everything that's spatially correlated. And that gets rid of nearly everything. The deformation, spatially correlated, at least for geophysical systems. The atmosphere, of course, the orbit as well. Part of the Hopper or EM error is also spatially correlated, but not all of it. There are different ways you can do this, but essentially you can just take the average phase, so a random point. So in one sort of very simple approach, you can take pixels around the phase. In a more sophisticated approach, you can filter this. Essentially, you're just trying to get estimate the spatially correlated phase for every pixel or all the pixels around. Okay, so if you do that, it's with just the noise and this part of the DM error that's correlated, sorry, that's spatially uncorrelated. But it is correlated with perfect baseline. Already, you can take the same approach to estimate this DM error or top error. And it's just by looking at how the perpendicular baseline and the phase differ. In this case, it's not the phase difference between 2 points, but the phase of a point minus the spatially correlated. Basically, a similar idea, except in this case, you can subtract all the information as well. So it's only a 1D problem. But 2D problem, so it's a little bit easier. Yes?
So how do you subtract the deformation when isn't that what we're trying to calculate at the end?
Yeah. Okay. So that's a good question. Why do you subtract the deformation? So in this first part, the idea is just to characterize the weights to identify the distance. And then you go back to your original phase again, which includes the definition.
So how do you subtract it if you don't know what the value of the definition is?
Yeah, so you don't know what it is, but the idea is just to subtract everything spatially correlated. So you'll get the deformation and the atmosphere and the orbit. So it all gets lumped in together. It's not being separated out. So, the way you estimate that is by just estimating the average phase. And so there is a trick to that because, of course, that's the picture here. Right, this is the point which you're interested in testing. You take the average phase of all the other good pixels around it. So the trick here is you don't know at the beginning what the pixels are, because there'll be lots of pictures around here which just have noise as well. You want to avoid using those. So actually, it turns out using picture to do that. So you can take a guess in the first iteration which pixels might be reliable. And then when you've done this process, every estimated noise in every pixel, then go back and re-estimate it. Know better. Yeah, so this is this point here. Re-estimate it and iterate this 2 times. So actually after about 3 times, so all right, so what at this stage we haven't estimated deformation at all, but what we have estimated is kind of level of noise at every pixel. So that's characterized by something called the temporal coherence. So essentially, temporal coherence of 1 means there's no noise, and 0 means there's only noise. So to try and identify, to pick a sort of threshold value of temporal coherence for the good and bad, the trick for that is to also generate a curve using random phase. So if you just take random phase, although you've actually got 0 coherence, when you estimate it, you won't get 0 coherence. You get some value higher than that. And if you then compare your actual PS candidates with your random data, see you're going to get higher on average. To pick some threshold value such that you've hardly got any green to be random. And you can vary that around. How do we actually start? Is it a hard button? No. I'm looking at you. Who's running this show?
No, the person, but to, like this is last thing before.
I just can't remember what time I actually started, but it's already 10 minutes. Okay, so this is using this technique now applied to log valley. So all of these points represent pixels which have low noise. Such that only about 5% or so are going to be. This is the point where you now go back to the original phase. So you add back in the definition to orbit errors. The only thing at this stage to subtract off is this uncorrected. You've already estimated it. Okay. At this point, you go back and you add everything back in, and you're looking. This is just looking at the phase for every of those programs. So this is the primary program. You can see it's in the middle phase. So that's zero phase master. So in all the others, you can see this deprivation, which I'll show you in a moment, not steady state. Okay, so now you have your deformation, the atmosphere, and your orbit errors are all in there. That's at the moment. The next step is actually to unwrap the phase. So with the temporal model, you kind of do your unwrapping when you do your estimation of velocities. But in this case, you haven't done that, so you have to do it in some other way, and you don't think you'll go into that. Suffice to say, if you have time series of data, you can do it better than you just have single. Okay, so these are the data that are now being unwrapped. And you can see the deformation signals, which looks like it's negative one way and positive the other way. So actually the final step is to now to try and separate out deformation counts. So you can estimate the correlated part of the DM error in the same way as before, but so correlation with the baseline. And all these things are very easy to do when you have unwrapped phase. It's not such a problem. And then, as in the other approach, you can try and separate out deformation from atmosphere. Okay, so this has been re-referenced now to the time here, and basically you can see this series of time series of deformation. This is the average velocities on the right. So it's just a comparison of two different approaches. So again, this spatial correlation approach tends to be better. And this was just a comparison of the InSAR in red to some other data. You can see it's not behaving in a linear way in time. That doesn't really matter. That's just, I won't dwell on that, but that's, you are able to estimate how well you're doing. Just briefly, differences between these different approaches as well. I guess the spatial correlation approach just works more generally, but if you really want to be rigorous about it, the temporal model should give you some results. But here's a comparison carried out by someone else using one of these temporal correlation approaches and the approach using spatial correlation with some region in Spain. And you can see in this case there were more points picked for this particular region of this. And that's because these points are behaving very rapidly. Okay, so summary of Pierce's approach then. First of all, you're relying on these pixels that have very low decorrelation throughout your whole series of images. You can reduce your non-deformation signals by modeling and filtering, and this works very well in urban environments. So people comment, I mean, you'll see these techniques being used all the time in open environments. Use this, but they're particularly good if you're interested in the local deformation going on in cities. Not normally, well, it can be related to geophysical problems. Okay, so I wanted to move on to part 2, which are these small baseline. I showed you this already. This is a distributed scatter pixel on the right, the PS pixel nicely. But what if we wanted to use these distributed scatter? Do that? Well, yes, can. Basically, what we try and do is pick interferograms where we minimize either movement of these scatters within the resolution cell or minimizing changing angle or both. So in practice, you might form a network of interferograms like this. This is time, the x-axis, and same kind of plot I showed you before. In that case, it's radiating out to the front image. Now we're making multiple interferograms, each of which are short in the sense of temporal baseline, also short in terms of perpendicular baseline. That's because perpendicular baseline is essentially changing. Keep that small. You minimize the change. So this is for Sentinel-1 data, and you'll notice actually, the numbers may not be in meters, but actually all of these are very small. So if you're looking at other data from other satellites, you may find much larger numbers, and you have to worry about that. But in this case, we can more or less just make those which are small in time. Okay, so in this approach, you make multiple interferograms, as I just mentioned. You multi-look each interferogram, which I hope you covered this morning as well. The multi-looking is just adding up phase of nearby pixels. So it reduces your resolution, and it also reduces. And you unwrap the phase for each interferogram. And you can do this in 2 dimensions. The last step is then to find pixels which are spatially coherent most of your interferograms and invert them in some way. It comes into deformation. So these steps, this is just conventional InSAR. So we learned about this first 3 steps of conventional InSAR. That's one of the nice things about this approach. It's actually quite simple. The only bit you don't have to worry about is how you invert or order interferograms to try and get times in placement. And there are various different approaches to this. I guess the SBAS, the small baseline and subset method, which is one particular algorithm, one particular small baseline algorithm. In this case, they used singular value decomposition insertion. There have been multiple other approaches, squares, strain squares, norm, well, and there are other things as well. But essentially, once you've got a bunch of unmapped data, you can throw any technique in version to find data. What I'll draw your attention to in particular is this mixed SBAS, because that's developed here within COMET, and you'll be using that tomorrow. I should have mentioned before, you'll have a go at stamps between the spatial correlation second of this, and we also have a go at mixed SBAS. Okay, so when you hear about SBAS or mixed SBAS, NSBAS, the AS bit stands for and subset. That means you don't have to have a fully connected network. So in grey here, we're showing a fully connected network. It means you can integrate many points with any other points fully connected way. But in principle, we form a sub-networks, so it's in by these red lines here, which is no longer fully connected. That means you can't get the phase of this point to this point. No integration. But if you make some assumptions about your temporal behavior, you can still use it. Yes?
So do you won't miss out like dates with gaps?
Yes, that's right. So there are gaps, so you're missing out. But it doesn't mean you wouldn't be able to get an estimate particular time. If you wanted to get an estimate of the overall rate, still.
Yeah.
Yeah, but you do have to make some assumption about what's happening. You don't know what's happening in Korea here, for instance. So you have to build in some assumption. Yeah.
Is this mostly to reduce computational costs or to reduce the chance of
It's the latter. So this is done on a pixel by pixel basis. So you might form more, or you would form more than first. When you come to look at individual pixels, you might find that this particular one is just noise. There's no signal. You can't reliably toss out for that. It's not for computational costs. Ideally, you'd like to have a few. In practice, sometimes you just can't. Okay, so LIX, again, just mentioned. LIX-FAS has the AS as well, so LIX-FAS is already the approaches, still give you an estimate. So one nice thing about the small baseline approach as opposed to the DS approach is you have some redundancy. So in principle, you have 3 images, form 3 interferograms. Then summing up this one and this one should give you the same phase as the interferogram. Okay, so you can take different paths around the network to get the same result in principle. So if you try that, if you look at one of these triangles in baseline space, and you don't get back 0, it could be you have an unwrapping error. If you have an unwrapping error, the difference should be a multiple of 2 pi radians. It's like 360 degrees. And so a large difference in enclosure would indicate you have an unwrapping error in one of your interferograms. Looking at one of these triangles alone, you wouldn't know. If you look at multiple triangles, find drill down into which interferograms. That's when you then go back and start plotting these interferograms, because you don't trust the phase dynamics. Has to be said though, you're taking multiple pixels. You'll never get 0 back. You'll never get 0. And that's because of contribution both from noise, so noise adding up in different ways, you do multiple interferograms, but you can also get some systematic biases. So just talk any detail about that, but it's something to flag up actually. These systematic biases bias positive. So, in practice, when you do this, you calculate these phase values, and you only identify an unwrapping error if it's larger than the amount. So it's getting close to 2 pi radians, so 4 pi radians. So here's a result using LIX-FAS, one approach that you'll try tomorrow, with a comparison to GNSS to show you that it's a very nice result. So the kind of background color are the results from InSAR, one, and the circles are showing results to GNSS in the line of sight. The information from GNSS has been transformed into line of sight comparison process, and you can see it compares very nicely. Also, if you look at the detail of the temporal history, it compares very nicely. So this figure here, so the grey and the blue dots are showing comparison between InSAR and GNSS in time. And you see a very regular deformation that's going on. In blue, you can see the groundwater the changes. And here's a large scale application of LIX-FAS. This is the whole of Turkey. So looked at both ascending and descending data from the whole of Turkey. In this case, I'm just showing you the losses and the long term. There's also lots of other signals here. Various signals due to structure here as well. Okay, so that's kind of just to give you a brief overview of the standard or baseline approach, and it actually doesn't take very long to really standard conversion at the end. But there are some additional things that you can do. So you can do your phase unwrapping in 3 dimensions rather than 2 dimensions. So you take your 3-dimensional series of time series of images and try to way. Yeah, this is you can't tell it, but this was done with the 3D unwrapping. This is showing again it's water extraction. Regional terrain, very high rates there as well. And another variation is looking at processing single liquidity. So processing full baseline way, but without doing the bottom. And so there's a number of different, or a couple of different ways of doing this. You can draw your attention to this one again because it's included in the stats. All right. So in the stats approach, basically exactly the same as this approach. It's applied to these small baselines. Okay, and then they're unwrapped, and then in the case of stamps, so here's a result from that. This is the result from the volcano in Iceland, matter. This area window data will raise may have done this morning, but you can do InSAR and Iceland. You have very short results on Iceland. Okay, so this is a volcano. In this case, what we're seeing is the intrusion of magma back in 1999, 2000 time. This is just looking at one of those interferograms, and it's a comparison of the PS approach left compared to the small baseline approach right. And of course, you get very much the same signal, as you expect. It's the same signal. What you find is that some points say can be haze, can be interpreted quite nicely either as scattered or as small baseline. But some only behave well for the other. There are many more points that behave well as small baseline, which is what you'd expect. You'd expect most scan or most pixels in these kind of broad environments to be distributed. You expect to pick up more small baseline. But it seems there are some you do better, or you say you reduce you increase the signal noise by yes. Well, this is showing the broadly pixels expected by one method or the other. So both showing you the coherence from using small baseline approach versus the coherence. Yes. So for those that were picked by both, shown in purple, getting similar coherences. You can see blue ones, which are small baseline ones, high baseline approach. Yes. Point is, I guess, that these two things can be quite complementary. So you can just take one approach or the other, but actually you take both approaches and combine them. And here's an example of that. These 16 data applied again in Turkey, actually. Applied to some early data and something. Oh, sorry. I think actually that previous one I showed you was just four bases. You can combine them like this. I don't go into too much detail about how you do it. You get a result like this. So again, this is the result for a similar time period. You end up with more points. Approach, you end up with higher points. Okay, stop there. Just to summarize then, there's two different approaches, time series analysis, commonly used in InSAR. PS, approach, baseline approach, and they're both good for different things. would say, in general, practice for computational reasons as much as anything. If you can get away with using a small baseline approach on multiple data, that's the approach. Cheap computationally, and and also you will get 4 points in general. If you're interested in higher resolution processing, or if you're interested in processing over cities in general, you're likely to use it. Okay, but in both cases, you can reduce non-deprivation signals in the same way, actually, just by swapping time. Both approaches are possible, and I guess think in the practicals. Is that right? You'll have a go at both?
In practical, we will yes.
So PS and stamps, but then there's lift pass as well.
Well, but the practical will be.
And that'll be it. So you'll have probably different data sets.